Right, I want to make a clarification. Remember that in this previous example, n equals to 8. Why did I change it to 3? And the reason is because in our example, the values of x4, x5, x6 and up to x7 are all 0, and hence I write it as 0 to 3. Of course, if you really want to do it as n equals to 0 to n equals to 7, there's no problem. But you're basically multiplying by 0, and hence you're summing zeros. And that is why I did that. Okay, now with that, we can now go into the next example. The next example is to convert the DTFS to the DTFT. Remember, this is the problem we want to solve. In this example, we've seen that if the signal is periodic, we can calculate the DTFS. We can also use the DTFS coefficient Ck and represent it as DTFT, which is x omega. What's the difference? DTFS, the values are from k equals to 0 to n minus 1. What about x of omega? Omega is continuous. All frequencies from minus pi to pi, 0 to 2 pi, or in fact from minus infinity to infinity. Later on, you realize that x of omega is 2 pi periodic, but the problem is that x of omega is a continuous function. So how do we convert Ck into a continuous function is the problem. This equation or this conversion is already partially explained to you. We are going to use the deltas to represent the values that are non-zeros. So at omega at 2 pi n over k are non-zeros. We say that Ck's will exist at this omega, and where there are no values, the values are 0, then in fact we don't even have this delta sitting here. So the answer is to convert Ck's into x omega, the DTFT representation, we are going to multiply the Ck's by 2 pi and put the deltas at this particular frequency. Let's see how we do it. So this is page 8 of our slide. So what we did was that we first calculate Ck's, which is here, the magnitude and the phase plot, and this is k from 0 to 7. What we then do is that we convert the horizontal axis first. So this is the horizontal axis is k. We convert it into omega. And then you say, oh, it's still k is equals to 0 to 7. But what it does is that the real horizontal value should be 2 pi times k divided by n. So over here is still 0. Here is 2 pi times 1 divided by 8. Here is 2 pi times 2 divided by 8, and so on and so forth, until the last one is 2 pi by 7 divided by 8. And of course, if you are asking what happened at the point 8, is 2 pi by 8 divided by 8, which is exactly at 0 to 2 pi. Right. Now, the other thing which we wanted to say is that, well, we are putting arrows or delta functions at the locations where there are values. So you can now see the arrows over here. So only at this point there are values, and in anything in between there are no arrows, means no delta functions. So the delta functions are sitting at 2 pi times k divided by n, which is 8. Now, what values are there? It is the original Ck value. So if you compare this plot and this plot, they are same value, but because I have said that these values are multiplied by 2 pi. So it should be 2 pi times c, in this case is 1, this is 2 pi times c2, this is 2 pi times c3, and so on and so forth. So this is the magnitude plot, and of course in the phase plot, we don't multiply by 2 pi. The phase plot is not multiplied by 2 pi, the phase remains the same, only the magnitude is changed by 2 pi. Okay, so because if you look at the equation carefully, it's 2 pi times ck, but only the magnitude is changed, the phase will not be changed. So this slide in page 8 shows how we convert the C case to the DTFT representation of a periodic signal. Thank you.